Okay, let's get started. So today's recitation is about threading and thread synchronization. So your proxy lab is out. It's due a week from tomorrow. That's December 8th. And you can use up to 2 late days on it if you have late days remaining. If you haven't started yet, that's okay because you were on break, but you should get started here soon so that you have time to do it. So we're going to talk about proxy lab, some of the recap of some of the code samples that we've given you, and what's things to look out for in those that are relevant to your proxy lab, some debugging tools that'll help you, and then we'll talk about concurrency with respect to threading. We've already talked about concurrency with processes, so now we're just extending that discussion. So proxy lab, as I said, due Tuesday. We use a max of 2 late days. You should make it robust. So one thing that you may have noticed if you've already started on it is you can get a proxy lab that works on a lot of simple web pages. Maybe it works on example.com, maybe it works on the CMU website. But then you go off to some other thing, something that has like videos on it, or crazy flash ads or something, and then it'll just crash. And that can happen because you can see all kinds of random bytes when you're downloading internet pages. And so you should take care to make sure that you're not expecting anything more standard than what the actual standards guarantee. So you get some guarantees about what a valid GET request looks like. If you get something that's not that, you should be able to correctly handle it and not crash. But you shouldn't be assuming that you're going to get anything that isn't part of the actual standard, which we describe in the book and the handout, what you can expect. So some of the files you can get from the book and the associated code on the website might be useful for you to look at because they do implement a full server and a full client. This is the Echo server. So the Echo server, if you remember, was the server where you just, anything you send it, it spits right back at you. Not very interesting. One thing that's notable about the Echo server is that it was sequential. So in your proxy lab, you're writing a concurrent proxy. So the proxy can handle multiple connections at once, and you'll do that through threading. If we look at the Echo server, we see that it has this, ability to only handle one thing at a time. So here we're just, we go into a while loop while we're handling the connection we have, and we can't do anything else with the other connections while we're doing that. So we can echo a connection that we're currently making, and we only make one request at a time. So we're only able to handle one thing at a time, and then it's not till we close it that we can go and make another connection. So this is this might be a good place to start in terms of understanding how things work, but this won't be enough to get your actual proxies going. You'll have to add concurrency to this because if we could use Telnet if we wanted to explore how the Echo server would react to multiple connections, and we could see that if we run the Echo server and we connect to it with one guy, then that guy is consuming the connection, the only connection that the Echo server can handle. And so then if we tried to connect with a second Telnet session while the first one was still open, we wouldn't be able to connect. And so, in your first version of your proxy lab, it will probably look like this, where you won't be able to handle multiple requests at the same time, but that's something then that you'll have to upgrade, and you'll be doing that through threads, which we'll talk about. Does that sort of make sense why the Echo server only handles one at a time? Does everyone see in this code? So more advanced debugging. So I think I mentioned this last week, but one of the things about Telnet is that it does require you to type in that whole GET request by yourself manually, which can be annoying. It's good for debugging malformed requests because you can actually generate whatever malformed request you want. The automatically generated ones will hopefully actually be correct. They should be if the tools are working right. So once you're actually going to test something and you want it to be a correct request, then you can use curl instead of telnet, and that will form the request for you. And this is how you can use curl with your proxy. This would be for if your proxy were running on the computer local host with a port. You can replace this with a Shark machine and the actual port number in order to get it working with your proxy and then whatever website you want to connect to. Now here's an important warning in red down here. Take heed of this. This is a mistake that many people will make initially with their proxies if they're not paying attention. Remember that binary data is not the same as text data, just normal strings. And the internet does have binary data in it. So if you've got an image on your page or a video or anything, anything other than just the text of the page, it might have things like 0 bytes in it, a byte that's just 0. And that does not mean that you're at the end of the data. It just means that somewhere in the middle of it there was a 0. And so you have to be careful when you're operating on the bytes you're getting back from a server to not be using the string functions which assume that when they see a 0 you're done, because that's not in general the case for the internet. You will quite often see zeros in the middle of the content. And so you should be working with all the functions that are used for arbitrary memory. So in the CSAPP package, there's functions that take arbitrary bytes and don't assume it's going to be an all-terminated string. In the string.h, if you're using those functions, there's the functions for strings, like strcopy, which assumes it's null terminated, and then there's the functions for arbitrary memory like memcopy, which don't make that assumption that when you get to the null byte that it's the end. So you should make sure that anywhere you're working with these arbitrary bytes from the internet that could be something other than an ASCII string terminated by 0, you're using the correct functions so that you don't just end up with half a web page, which will probably end up being garbage when you try to look at it in your browser. Certainly won't be correct. Okay. So any questions about that issue? It's a common mistake that people will make, but it's not too hard to fix once you understand what's going on. So now let's talk about threads. So before we talked about processes. In Shell Lab, you used multiple processes. They were running concurrently. You'd have all of your background processes and then maybe one foreground process. And they'd all be running at the same time, interleaved arbitrarily. And you had to take care to make sure that you didn't introduce race conditions, that your shell handled all arbitrary interleavings correctly. Threads are very similar, except that more is shared in threads than in a process. So you still get that arbitrary interleaving. You might have things running in parallel. If you have a multi-core computer, you can actually be running 2 threads at the same time, in the same way that you can run 2 processes at the same time. But we actually only have one process now. So one process can have multiple threads associated with it. And that gives you different logical flows, but you're still sharing the same memory underneath. So now they're not splitting off the memory anymore. So you still have context switches. In the processes, you would switch between processes, and that was called a context switch. You still have that. There's less context to be switched now, so they go faster. It's faster to split into multiple threads than it is to fork off a new process, and it's faster to switch between them, which is one of the advantages. So threads do have their own thread ID, same way that processes had a process ID, just so we have just a number that allows us to identify them uniquely from each other. Every thread has its own stack and stack pointer, so the local variables aren't shared between them whenever you're in a function. Their own instruction pointer and registers. So as you're tracing through the assembly, it's not like one thread is going to come in and start overwriting the other's registers because you had a context switch. That would make them impossible to use. But what they do share is they have the same code. So you don't make a copy of the whole binary to have a new thread, and they have the same heap and open files. So anything you're writing to the heap can actually be seen between threads. So this, and anything you're doing with open files can be seen between threads. So this is where we have to care about arbitrary interleavings. If we're using heap allocated memory, we have to make sure that whoever's writing to it is writing to it appropriately, so that we don't have multiple threads creating race conditions with when they read and write. Because the classic example of a race condition that happens is one thread reads from heap allocated memory, then another thread writes to heap allocated memory, and then the first thread writes to the heap allocated memory. But really what he should have been writing needs to be updated for the fact that there was a change to it after he read it. And what he's writing depended on what that was, and so now you've sort of lost part of what was happening. We'll see an example of that. So the way we'll be doing threadings is with the pthread functions. So the pthread functions are just they're the standard way of doing threadings on modern Linux machines. So there's a function called pthread create. That's how you're going to be creating threads. And what it does, it takes in a variable that allows you to store the new thread's ID, so you have a handle to it if you want to do anything with it later. Some attributes, which will always be null for here. For this course, we never use any of that. And then you also have the function that the thread is going to run. So this is a function pointer. Have you seen function pointers before in 122? If you haven't, we talked about them in the C bootcamp way back at the beginning of the year. So anyone who hasn't seen those can refer back to that if you want to see how they work and what the syntax is for that. And it's a function pointer to a function that takes in a void pointer and is void and returns a void pointer. So it's just one really generic input and output. And what that void pointer coming in can be, it could actually be a real pointer that we cast to the correct type afterwards. Pointers are, we could actually just put an integer in there if that's all we wanted to pass in. We could cast the integer into a pointer and cast it back. That's okay, because integers are 4 bytes and pointers are 8. Whatever we want, but that's the function that the thread is going to execute when it starts. So instead of just continuing on like fork did with the same control flow in both processes, it actually executes this function. And then, so you point to the argument. Yeah, so then you can, if you want to pass multiple arguments, you have to pack them up in a struct. You only get one passed into the function, so you have to pack them together if you want to pass multiple things in. So this is where you put that actual argument that this function is going to get. So that's how you create a thread. So now let's actually use threads for something. So this is sort of a boring example. And it's not something that you would do quite this way in practice, but the point is the threading, not the details of the thing we're trying to do. So all we're trying to do is just add up a bunch of numbers. We have an array of numbers and we want to add them up. And so, before you learn threading, this is how you would do it. You just write a for loop that adds them all up. That's actually pretty simple. It's like 3 lines of code, pretty clear what it does. But it's slow. You have to go through every element of the array. Maybe you have a great computer with 4 cores and you want to go 4 times faster or something. So this is how you would do it with threads. So what we're going to do, this is going to be the function that the threads will execute. So it takes in a void pointer and returns a void pointer. And we're going to get the ID of the thread out of that argument we got. That's what we're going to pass in, is just the ID. So we cast it to an int pointer and then dereference it. So we're assuming that this points to some int. That's how we're going to set it up when we make the call. And then what we're going to do is we're going to chunk up the array into pieces based on some constants we've defined, the number of elements per thread, and how spaced out they are. And so we'll figure out where this thread's chunk of the array starts and ends. And this thread will be responsible for adding up that chunk of the array. And these details aren't really the important bit. And then, we figure out what index it's going to write into. So then we're going to write into an array of partial sums. So we take the big array, and we're going to take chunks of it and sum them up and put that into one element of the smaller array, and then the sum of the smaller array will give us the sum of everything in the big array. Right? So we go through, and once we figured out what this thread's piece of the big array is, then we're just going to add up that piece and put it into our other array. And then we return null. We don't need to return anything because the information we wanted is in this array that we're creating here. And so then we're going to figure out what number of elements per thread is. We're going to create a bunch of new threads, and we're going to use thread fun. Each of them is going to run thread fun to sum up its elements, and then at the end, and then we want to use join. So then join is the function that actually brings the two control flows back together. So then once they've all finished, we want to make sure that we've collected it all up, and then we can continue on with the main routine. Yeah.
Why we're looking through 10 threads? Why don't we just need one thread to that one function? Or why are there multiple threads?
So each thread will run this function once. And what we're doing is we're creating a bunch of threads so that they can all run that function at the same time. So each thread here, let me... Yeah, so we've got a big array. Got some big array, a bunch of stuff in it. What we're going to do is we're going to cut it up into pieces. We're going to say okay, cut it up into pieces of 4, and then there's some excess. And we're going to say, okay, thread 1 will sum up this part. And we have a smaller array down here. And so thread 1 sums up these 4 elements and puts it into this. Thread 2 puts it into this, and then thread 4 sums this 2 and puts it into this. And then we can just sum up this array, and the sum of this array will be the sum of this array, because these are the partial sums.
And that's the join.
So the join function is when we create a thread, now we have two control flows happening concurrently. Each thread is running concurrently. What join does is it takes the two threads and it puts them back together into one. So now that we only have one thread running again. So it waits. The join waits for this child thread we have to finish, and then now we can continue on with just one thread. Because what we want is, once we've got these 4 partial sums, is to just continue on as one thread now. They are original main thread. Yeah.
But is there a max number of threads?
There is. It's like a system-defined constant, and it changes from system to system. I think the default is somewhere in the thousands or tens of thousands. You'll never run into it in anything in this class, for sure. Yeah.
If you have a big array, would it just break it up once, and then once it sums it, sum the element of the summed array? Would the threading only happen once?
With the threading?
If you have a array of size 200,
Uh-huh.
and if you're dividing into chunks of 50 with 4 threads,
Okay.
and then you sum all those chunks. So, wouldn't it be more efficient to break it up into smaller chunks and have more threads depending on what the size of the array is?
Smaller chunks. Yeah. So this one just has some constant number of threads,
Yeah.
and it breaks it up into that all the time. Yeah. If we were really, if we really wanted to write an actual efficient parallel adding, then yeah, we would care about how big how big is the array, what's our hardware, because it really depends on your hardware. Your hardware has some number of cores, and ignoring hyperthreading and all that, the number of cores is the most you can run in parallel at a time on your CPU. So if you have a 4-core computer, you can only ever be running 4 threads at a time. Splitting up into 400 threads isn't really going to make a difference. But if you have a big distributed system and you've got 1,000 cores available to you, then you can actually have 1,000 threads running at once. And it's there's benefit to splitting it up into that many if you have a large enough data set.
Wouldn't it be better to just write a generic function that anyway splits it up into assuming an infinite number of processors?
Assuming an infinite number of processors?
I mean, wouldn't that be the best case scenario? Like, isn't it better to write an algorithm that does that than, takes a constant? I mean, sure, if it was 4-core, it wouldn't matter, but, it's still better to have that algorithm run on the 4-core than...
Assuming an infinite number of processors, that's that's the sort of thing you do in 150 and 210 when you're doing span calculations. You assume infinite number of processors. The other thing you're assuming there is that there's no overhead, that creation and joining is free. In reality, creation and joining is not free, and so if you divide things too finely, it actually costs you more than just doing things sequentially. As the size of the data increases, that becomes vanishingly small. So asymptotically, it doesn't matter, but on small examples, and small quick things like this, it does make a difference. Because adding is actually pretty fast. Adding is just one assembly instruction, right? Are there any other questions about this example? Okay, so we join all the threads back together as they finish, and then what we want to do is we want to add up the results, and we want to then add up also these leftover elements. So in this case, what we actually did to better match this example, since we did number of elements divided by number of threads with integer division, what this would actually look like for this example is this leftover bit doesn't get its own thread, and then we added it on at the end. So we added up these 3, and then we went back and added these 2 guys to it too. And you could do it the other way, where you just have a thread that has fewer elements. It'd be a slightly different setup. Either way works. And then you just return, you return that sum in the end. And so now we've added up all of our numbers. So what's good and bad about this? So what's good? We could make it faster. If we do this right, if we have a lot of numbers that we're adding up, multi-core computer, maybe we just made our adding function 4 times as fast, and that's great. We can also get with better cache performance if we do threading the right way. But there's also bad things. This is significantly more complicated, right? I think this, we all agree that this is easy. We could all write this. And you look at this, you know what it does, you know that it's right. You're not going to make a mistake writing this. If you do, you'll catch it right away. If you write this, though, this is a lot harder. You might mess it up, you might have a bug that's hard to catch. It might be a race condition. That would make it really hard to catch. If someone else writes this and you have to read it, it's much, much more difficult to figure out what they're doing. So that's a disadvantage. It's harder to write, it's harder to read. We made it faster, but there was a cost to that. And also specifically the shared resources. So in this case, it was okay we didn't have to really deal with issues of shared memory because everyone was just writing to different elements and reading from different elements in this array. No one was touching the same memory, none of these threads. This thread only cared about these here. He would read these and write to this. This one would read these and write to this, and read these and write to this. So none of them ever wrote to the same thing. None of them ever even read from the same things. And so all of the accesses were mutually exclusive. Everyone was the only person who accessed whatever they accessed. And then that was fine. We didn't have to worry about resources, but in general, you might actually be dealing with shared resources, and then that would become a problem. If like they were reading from this array and updating it in multiple threads, had access to it, that would be something we'd have to deal with. So, okay. So here's another example, same thing where this example is a little bit, it's a simple example. It's not particularly something you would do quite like this, but it gets the point across of the shared variables. So what we're doing, so let's see, so the thread, let's see, we've got a total, and then we write a function increment, which is just going to add to this variable repeatedly. So this variable is shared memory. It's a shared global variable. All of the threads have access to this. Okay, so what do we do? So we're going to have two threads, and we're just going to make both of them run increment. Increment is just adding 1 over and over and over. So we've got two threads, and they're both adding 1 to the same variable, and we're trying to get it to, each one is going to add 100 times. So if this works, we would expect it to spit out 200, right? Thread 1 has added 100 to it. Thread 2 has added 100 to it. We get to 200 because we started at 0, right? So, okay, so, well, what happens if we even set it to, something smaller? So we're not even going to go all the way to 200. Okay, so these get interleaved arbitrarily. We don't know who's going to get, access it when. It could any order could happen. So here, thread 2 gets it. It reads it. It says 0, adds 1, and writes it. So now it's 1. And now thread 1 is going to read it, and it sees 1. And now thread 2 is going to read it, and it sees 1. And so thread 2 adds 1, and it writes it, and now it's 2. And thread 2 writes it, and now it's, well, actually, no, in this case, now thread 1, after it writes 2, reads 2 again and writes 3. And now finally thread 2 gets around to writing the 2 from when it read 1, and now it's 2. And so sort of this is maybe a little confusing, but sort of what's going on is we have a situation where, the one thread reads it, and then the other thread reads it, and then this thread writes it, and then this thread writes it. And so what we wrote was the increment of this, but it's been updated since then. And we wanted to make sure that, we wanted to try to get it so that all of the threads, that all of the updates, were using each other. And so what can happen then is you could work out a pattern of reads and writes that gets you any number between 101 and 200. Right? Yeah, depending on when they access it. Because maybe what you have is something where, this would be worst case scenario. This guy reads it, and this guy does 100 reads and writes, all of his, and then finally this guy writes it. And then he does the rest of his reads and writes. And then all of these just got thrown away. Everything that thread did. So, if they go back and forth perfectly, we'll get all the way up to 200, but we could, depending on, stuff like this, see any number in between. And if you wrote this program, I think this might even be one of the programs that comes with the book, is you can actually run it and just see the different numbers it generates. It'll just generate different numbers depending on how the scheduling happened to run that time. And so that's a problem, obviously. In general, we don't want our programs to be just completely non-deterministic. We want some sort of control over what order things are going to happen in, so that we can make sure that those updates to the shared resource are correct. And so the solution is something called mutexes. So mutex is an abbreviated form of mutual exclusion. Only one person gets access at a time. And so what we're going to do is we're actually going to only allow one thread to have access to a resource at a time. And the thread just won't do anything until it gets access to the resource it needs. It'll just stop execution. Then it will use the resource, relinquish its access, and continue on. And the next time it needs it, it'll just stop until it gets access again. It has to wait for everyone else who's currently in line to access it. So how does this work? So there's some functions, part of the pthread. Mutexes are part of the pthread library again. So you can lock and unlock with a mutex. So you have a mutex, the mutex type that we just called M. And before we actually go to add to this total, what we're going to do is we're going to acquire a lock. And if someone else is using this mutex, someone else has a lock on it, when we go to acquire it, then this hangs until we can acquire that lock. We don't get the lock until everyone else has relinquished use of that resource. And then we go and we do the add. And this is the critical section because we want to make sure that the read and the write happen without anyone else touching this variable in between. So we need the mutex around the whole read and write, and since it's a plus plus, that's actually just one line. But we want to make sure that the read and the write happen without anything sneaking in between, because that was what the problem was over here. And then after we've done the write, we've updated total, then we can unlock the mutex so that anyone else who's waiting for it gets control. If we don't ever unlock it, then now this thread is going to be stuck because it comes around and it goes and it tries to get a lock on it, but it's already locked by the previous time through the loop, and the other thread can't get it because it's locked by the other thread, and so then we just have deadlock and everything stops. So you have to make sure that you're actually doing the unlock, otherwise nothing will happen. That solves this issue. So does everyone kind of see what we did there? So the mutex is just it's a built-in way of handling these. And so then, okay, so yeah, so another thing, make sure to initialize the mutex first. So the mutex, when we just declare it up here, it's an uninitialized variable. As usual, that's not a defined thing. So make sure you initialize it first, just so that's initialized to the correct unlocked state. Okay, and so that's mutexes. There's a more general class of ways to deal with these issues called semaphores. So a semaphore is a special type of counter with some invariant. And in the case of mutexes, your invariant it's just 0 or 1. This is just a very specific case of mutexes where we only have two possibilities. But you don't always just want, a very simple, one person can access it at a time and no one else can touch it during that way of controlling things. Maybe you're doing something where you have reads and writes to shared memory, and it's okay to have lots of things reading it at the same time. The only problem is you don't want to interleave a write with reads or have multiple things writing at the same time. So as long as reading is happening, it's okay. It's just writings that you need to be careful around. Then you would want to, you could use something. You could do that with mutexes, except that then all of your reads are going to be happening one at a time. So if you want to make your reads concurrent, then you could use the more general semaphores and enforce the invariant that there's never a write going on while there's a non-zero number of readers. And you never have two writes at the same time. But you could have a semaphore and it can keep track of how many readers are currently using it so that you know that information. So, okay, so we have two functions called P and V. And P and V are the first letters of two Dutch words that I don't remember that are in the book because the guy who named these was Dutch. It's not really important what the Dutch words are. You don't need to know what the actual Dutch words are. If you recognize P and V, that's good enough. But what we have is P is the operation that locks a resource, so it decrements the value of S, and then V is the one that frees a resource. So then, we can enforce whatever constraints we have on how many people are allowed to access it at a time. And then an atomic operation, so the definition of that is just an operation that cannot be interrupted by anything once it's done. So you saw that a little bit in Shell Lab, that there were things that you knew. Well, I guess, I don't know, they weren't really atomic operations, but you saw a similar thing in Shell Lab where we worried about, what functions are safe to use where they might be, interrupted by signals. Is it okay to use this function if a signal might come in partway through executing it? That was an issue with, printing in your handlers in particular. Atomic operation is a similar thing. It's an operation where you know for sure that the entire thing will be finished once it's started, and you can't ever have like a context switch in the middle of it. Even if it's something that's multiple instructions to execute, the operating system guarantees you that it's never going to start executing another thread halfway through. And P and V are atomic operations, so you don't have to worry about a race condition where you start to acquire a lock, and halfway through something happens before you finish that. The increment operation, in contrast, is not atomic. Even though it's just one line, one symbol, it's actually doing a read and a write, and you're not guaranteed that you're not going to have something happen in between that read and the write. And that's what the problem was with that example, with the adding. Okay, so now we say, okay, problem solved. We have a way of dealing, with, we have this threading, and now we have a way with dealing of, memory issues if we have those, so that everything can be unique. But, there are problems with this. Locks are slow, especially if we're doing something like a mutex where we slow things down to, just one person accessing it at a time. If we do that in the wrong place, we might actually lose all of the benefits of concurrency, because if that's something that bottlenecks it, we might slow down to completely sequential somewhere. We talked about that could be an issue with your, if your cache for your proxy lab was completely sequential, even if the rest of the proxy is concurrent, everything has to check the cache before it to see if it has to ask the server for the page or if it's just going to load it up. So if you had a sequential cache, you could make a bunch of concurrent requests, but then they all get lined up sequentially to check the cache, and you're better off than if you had just done the requests sequentially. So in the same way, if we have locks, we could, in any case, they're not very fast, and in the worst case, they might actually turn things completely sequential again if we use them in the wrong place. So that's bad, and this is also a really bad way to sum up to 200. If you really want to sum up to 200, just use the number 200. You know what it is. But even if we want to, this is a bad way to sum up to 200. Even if we actually want to add up all of the numbers one at a time, it would be faster in this case to just have one thread adding from 0 to 200 than to deal with the locks between the two, because these are slow. So one of the best things you can do is just avoid shared memory if you can, as much as possible. Try to make it so that the memory that the different threads are using is just naturally mutually exclusive and they don't touch each other's stuff. Then you don't have to worry about locks. You don't have to worry about protecting against race conditions with accessing that memory, which is good. Okay, and so that's, this is a simple model in thread synchronization where we're just making sure that they're synchronized in their access of this one shared variable. If you look in the book, you can see other models, reader-writer, producer-consumer. Reader-writer might be useful to you for your cache in Proxy Lab. Producer-consumer you won't really need, but might be interesting to read about just so you understand it. Okay, so here's another example. So this is synchronization gone wrong. Can you see that at all? No. Oh, man. That's really bad. I don't know if it's even going to come through in the slides on the video. What can I do? Maybe if I zoom in on it. Is that better? Okay. Okay, so what we're doing here, some of the comments are cut off, but I'll just explain it. So we've got a couple threads, and we're going to do something similar to the thing we shouldn't have done on Shell Lab. So we told you, don't just sit in a tight loop and do like a while true as a way of, waiting for your processes to finish. We said like use sig suspend instead. So this is a similar thing that you don't want to try with threads. It's the wrong thing to do, where we say, okay, let's just say that we'll have a loop that goes through 500 iterations for thread 1 and 200 iterations for thread 2, and we'll call it spin wait. And so then what we'll do to synchronize our threads is that every time after we do something, we wait for a really long time before we do anything again, so that the other thread can do its thing, right? That way, if we space them out far enough, what we're doing is, we have these, reads and writes, and so what we'll do is we'll say, okay, do your read and your write, and then wait. And then this other guy can do his read and his write, and then wait. And then do a read and a write, and then wait. And if we make these waits long enough, then we won't have to worry about them overlapping, right? Something like that. Because, the problem is they overlap, so let's just spread them out a lot. That's not a good plan. First of all, even, it's not even guaranteed to work. The system might schedule things, it might schedule things that doesn't align with your waiting. And it could still be wrong. But even if it is right, and in practice you'd probably see it right if you waited long enough, you'd probably get it to work out. But what did you do during this whole waiting? You're just in a tight loop, burning CPU, but doing absolutely nothing. And so then most of the runtime of this threaded program is actually sitting around burning CPU, doing nothing. And if the whole point is making it faster, sitting around doing nothing does not sound like a good way to make it faster. And so, what we've ended up doing is, well, we're spending most of our time waiting around rather than actually doing calculations. And it's a waste of time and not even necessarily correct. So it's just bad all around. So don't try that. Try doing, use mutexes, use semaphores, use the proper way of synchronizing threads, because it's more efficient and it will actually work if you do it right. So here's an example of reader-writer. So I mentioned that was one of the other patterns, and we'll go through this quickly. That might be useful for your cache. Your cache might see something similar to this, because one of the ideas in the cache is that you've got this cache in your proxy lab, and it's okay for all of your threads to be reading from it at the same time if all that's happening is reading, right? Because nothing is changing. So two guys can be reading the same stuff, and that's okay. The only problem is when we go to write to it. We want to make sure that we don't, write to something that's currently being read and change it partway through the read. And we want to make sure that, we don't have two people writing at the same time overwriting each other. Either of those would be bad. And so, here we have three people reading at the same time from our cache. That's okay. Nothing wrong with that. Nobody's writing. This reader isn't reading. That's fine. But there's no problems here. But when this person goes to write, when this thread goes to write, we need to make sure that we're done reading before we start writing, because we don't want this write to overwrite something that's currently being read. So what we need to do is we need to set up our synchronization so that this thread does not acquire the ability to write to the cache until reading is finished. And so once reading is finished, then it's okay to write to it. But if someone tries to read, some thread tries to read while we're in the middle of a write, that's not good either, because then we don't want to accidentally overwrite what's being read. Or even potentially have the read go faster than the write and start reading things that haven't been written yet if they're accessing the same thing. So then we can't let the reader acquire the cache until writing is done. So once writing is done, now we can finally read it again. And we could have multiple people reading it again at the same time. So part of your goal in Proxy Lab is to set up a correct scheme that allows you to get multiple reads happening at the same time, but also make sure that you appropriately protect the writes so that writes and reads aren't happening at the same time. Does that make sense to everyone? And also, another thing to think about is also make sure that you don't have it set up so that it's possible for someone to want to write and to never get the ability to write because there's always people reading for the rest of eternity. That's a potential issue, is you want to make sure that the writer isn't just continually blocked by the fact that there's readers there. It should be that once these guys finish up, then we can actually do the write. So you'll want to think about how you deal with that. Okay, so right, yeah. So here's exactly what I said. So if we're blocking the writer, the writer is being starved of the resource is the term. He's starved of the resource that he wants to acquire, and you want to make sure that you don't have it so that you can just continually add more readers as requests come in and never actually give the writer the chance to write. Okay. So then just to finish up, a couple more things. So a couple terms, so you've probably heard these already. So this is deadlock. We've used this term before. So, we have this issue with these mutexes. Everyone just stops until they can acquire the resource that they want, with mutexes and semaphores both. And so it would be bad if we get in a situation where in order to free X, thread 1 needs to first acquire Y. And in order to free Y, thread 2 needs to first acquire X. So currently, thread 1 has a lock on X and thread 2 has a lock on Y. And neither of them can free the resource they have a lock on because they both need the other one first. But they can't get it because it's locked. And so what you end up is, this is called deadlock. Everything just stops because no one can continue on. And this is actually the reason why in your shell labs, you couldn't use printf in the signal handlers. Because what happens is the printf acquires a lock on the standard out that it's writing to. And so if you had a printf in your main shell and a printf in your signal handler, and the printf in the main shell is halfway through printing when a signal handler gets run, then that one has a lock on the terminal. And so then the signal handler tries to get the lock on the terminal so that it can print out its thing, and it can't because it's locked. And so the signal handler will never finish, which means that the main shell can never actually go back and finish its printing, so everything just stops. And so that's why you were given a deduction if you were using printf in the signal handlers, because it can lead to that's a race condition that can cause an error where everything just stops and you get deadlock. So that's an example of it occurring. It can happen with the same thing with these mutexes and semaphores. So yeah, entire program hangs. You just have to be, you have to be careful about where you lock and unlock, and make sure that you don't get into a situation where two people can't hand off their resources correctly because they're both requiring each other. And then there's the flip side, which is live lock, which is where the analogy is two people trying to get past each other in a hallway, and they both move left and right together forever, rather than one of them moving so that they can continue on. And so if you're, this would be if you incorrectly compensate for deadlock and they're just switching off resources in the wrong way, you might end up just flipping between states and never being able to continue. This is not as common of an issue. You'll see deadlock more often, usually in practice. But this is also something to think about, that you don't create this trying to compensate for deadlock. And so that's it. Are there any questions before we end? It's the end of time. Any quick questions? Okay, good luck on your proxy labs. Next week will be our last recitation. It'll just be review for the final exam.